Hello, this is our senior design showcase video for our project, which is to create an underwater glider. We are Team Black, advised by Dr. Tian, and our team members are Andre Benitez, Blake Breeze, Branda Nilon, Kimberly Dang, Muhammad Adawi, and Rolando Zulu. The goal of our project to create an autonomous underwater glider that can reach a range of at least 5 miles while having adaptive path planning and station keeping capabilities. During the mission, the glider can track depth, temperature, and onboard energy consumption. The data will be exchanged between the vehicle and a control device. And the glider is capable of carrying at least 1 kilogram. Due to the unpredictable nature of the ocean, the glider will have an object avoidance system. After investigation upon many engineering design options and criteria, the team has come up with a solution to the underwater glider project. The finalized project for the structure of the vehicle will be a single hull made from PVC with fixed wing structure, nose, and back of the hull made from 3D printed ABS resin. Many resins are built in the vehicle's hull, including accelerometer, LiDAR, thermocouple, and many others to help monitor navigating and proper function. The buoyancy engine is made from 4 syringes that intake and expel water at different pressure.
Hello everybody, my name is Kimberly Dang and I am the simulation lead for our project. The first simulation that I ran is the buckling simulation, which we ran at 1 ATM, the water and 2 ATM, the maximum amount of water pressure we expected our project to experience. When we ran the simulation, the results showed that there would be very minimal amounts of buckling and that they would occur near the ends of the wings and the ends of the tail cap. The second simulation that we ran is the hydrostatic load simulator, which produced similar results. The most amount of hydrostatic load would occur near the ends of the wings.
Hi, my name is Ron Nosoro. I'm explaining the CFD simulation using SolidWorks for our underwater autonomous glider. So starting with the simulation, we use SolidWorks to explain more of a laminar flow since we're testing where there's rarely occasion of any type of turbulence, meaning it will be easier to see and spot what are the highest pressure while gliding and going to certain depth. As you can see, the major part that impacted was on the wings. The wings show the major transaction of when the attack angle hits the water at the bottom, and impacts becomes about roughly of 101 with 590 pascals. And the top of the wing, whereas the blue part, it becomes 101 with 30 pascal.
Hello everyone, my name is Blake Perez. I am the structural design lead for the Underwater Glider Black team. The hull consists of several components, for example, the main hull itself, the bushing, the nose cone, the wings, and the tail. All of these components had to be specially designed to allow the glider to travel, as well as allowing for better weight distribution and managing the different subsystems of the glider. So while designing the hull, we first had to assign several different environmental factors. For example, the pressure that we were going to be experiencing. The pressure that we picked was water at about 30 feet, which would give us a very good idea of where we wanted the glider to travel, as well as allowing us to pick a rather substantial factor of safety. So for the hull itself, we decided to go with PVC as the material for its tight tolerancing, as well as its pretty manageable strength to weight ratio that we then cut to 3.5 feet. It was originally 4, but we found that by cutting it down to 3.5 feet, we were able to fit all of our subsystems together, as well as reducing the amount of weight that we'd have to put in the glider to actually make it sink and float and behave the way that we want it to. So with this hull, we also have ABS resin printed wings. The reason why we went with these wings is because the layer lines are substantially smaller, so it reduces the chance of delamination under stress. So with that, these wings actually bolt into the glider itself, and on the inside of the glider is a skeleton that is 3D printed out of PETG, which is also a rather sturdy material, and that allows the loading to be better distributed from the wings to the inside of the glider, as well as keeping the shape of the glider intact in the middle, because under certain high pressures with these bolts in place, it would cause the glider to warp. So having the skeleton in place was one of our decisions that we made as a team to better mitigate our environmental conditions, as well as something creative that I think that we did.
Our buoyancy engine is printed out of ABS resin, just like this cube. ABS resin allows for layers to be only a couple microns thick, which help to eliminate failure in layer separation from traditional 3D printing methods. In addition, some parts aren't printed out of resin just to prevent binding within the system. Our buoyancy engine contains 4 syringes, each with a capacity of 2 fluid ounces. This makes for a total capacity of 8 fluid ounces, which equates to about 1/4 of a pound in weight. They're all combined together by a 5mm lead screw and a coupler to a NEMA 17 motor.
Hi, my name is Brandon Nolan, and I'm in charge of the controls and data acquisition system for our glider. Our data acquisition system and controls is composed of 3 separate subsystems, all working in tandem to collect and store our data as our glider goes throughout its mission. One of the biggest design issues we ran into when trying to design this system is being able to store enough data for 5 nautical miles worth of range, which is a lot of data to store. A system to do so, 2 Arduinos as well as 1 Raspberry Pi in order to collect the data on the Arduinos and send it off to the Raspberry Pi, where we'll store it and eventually export it into CSV files for the end user once the glider resurfaces. On one of our Arduinos, we completely have all of our sensors, things like our gyroscope, our LiDAR sensor, as well as our thermistor, and even strain gauge for our pressure. And our other Arduino will have stuff like our motors, things like our stepper motor to control our buoyancy engine, as well as our servo motor to control any sort of turning on our rudder and all of that fun stuff. All of these will be working together and sending that data off to the Raspberry Pi, which will eventually store our data and which we may collect it towards the end of its mission.
Here we have the turning system for our underwater glider. It's made out of 3D printed resin where the bottom half has solid infill in it. That way the weight of the turning system contributes to the overall weight of the underwater glider. Inside we have our servo motor, and attached to the top half, which has less infill in it. That way the servo is able to turn the top half, and once activated, we'll be able to avoid any objects. It also has sealant inside of it, because even though the servo is water resistant, we don't want too much water coming into the glider. That way any of our electronics, especially the ones that are less water resistant, stay safe.
While testing the glider, there was many minor issues before making it work properly. There was the weight distribution, especially in order to find out our inclination for the glider to move forward. Using the specific attack angle needed to navigate, it was hard to find. In order to do this and fix this problem, we added diving weights in order to find out specific attack angle. Now, thank you very much for being part of our video, and we can tell that a couple things that we learned about the glider and autonomous gliders to be specific. From coding, calculating how the buoyancy works, different types of existing sensors, 3D printing, how to make different type of materials and how its stiffness will work, and improvement of the manufacturing process that we should add for future development of manufacturing of underwater gliders. Thank you very much for being part of our video, and I hope you guys enjoyed it.